Hello, Calculus. Today, we are going to attempt to learn some new material distance-wise. Specifically, we are going to learn the Fundamental Theorem of Calculus, Part 2. So if you love the Fundamental Theorem of Calculus, the Fundamental Theorem of Calculus, Part 2 is even better. And there's a really nice shortcut to this. This is actually the easiest thing that we're going to learn all year. Okay, Fundamental Theorem of Calculus, Part 2, we are taking the derivative of an integral, specifically the derivative of a definite integral. Excuse me, the derivative of a definite integral. So let's look at this definite integral at the top of the page right here. This is a definite integral. You've got your endpoints. Your left endpoint is 1, but this is new. Our right endpoint is a variable x. So the first thing we're going to do is we're going to solve this integral right here using the Fundamental Theorem of Calculus that we already know. And that's what this part of the note sheet goes through. So we're going to take this definite integral and we're going to use the Fundamental Theorem of Calculus and solve it. So the first step, of course, is to find the antiderivative. Well, the antiderivative of the sine is negative cosine of t, because there is a t right here. So the antiderivative is negative cosine of t, and then, of course, we use the brackets from 1 to x. So that's the first step of Fundamental Theorem of Calculus, which you all know and love. Now we're going to take the second step, and that means that we put in the right endpoint, the top of the bracket, and then the left endpoint, the bottom of the bracket. So it looks like this. We are going to take g of x minus g of 1. So this tells us to take the antiderivative and plug in x. So we get negative cosine of x. And then minus negative cosine of 1. All right, so now we're going to simplify that. We can't simplify this first term, so that's going to be negative cosine of x. But we can find, using our calculator, we can find this value right here. And when we simplify that, the cosine of 1 gives us negative 0.5403, and a negative is a positive. So we end up with negative cosine of x plus 0.5403. So that is the answer to our definite integral. Now, because one of our limits of integration, specifically our right endpoint, is a variable, we have an expression here instead of an actual number for area. So that's what this says here. The answer, negative cosine of x plus 0.5403, is an expression involving the upper limit of integration x. All right, so therefore the integral is a function of x. This picture right here kind of shows you what's happening. Here is our curve. Here is the area under the curve. Here is our left endpoint, 1, and here is our right endpoint, x. So this expression right here allows us to find any area, no matter where that we put that right endpoint. Okay, so now we're going to take the derivative of that. Okay, so we're going to take this answer to our definite integral, and we are going to take the derivative. Like we said, the Fundamental Theorem of Calculus Part 2 is the derivative of an integral. So here the negative comes along for the ride, and the derivative of the cosine is negative sine of x. So again, negative comes along for the ride, the derivative of the cosine is negative sine of x. And now we keep going, plus we know that the derivative of 0.5403 is 0. The derivative of any constant is 0. So let's simplify this. We get positive sine of x. That is our final answer. That is the derivative of an integral. Now I'm going to highlight this, and I want you to compare it to our original integral right here. What do you notice? Hey, I could have just taken this upper limit here and plugged it in right here, and I got this. There's our fun shortcut. You take your limit, upper limit, that is just a variable, and you plug it in everywhere you see t. Ta-da! How great is that? Okay, let's keep going. Okay, so that is what this kind of talks about right here. Here is our answer here. The derivative, g prime of x, is the sine of x. The answer is the integrand evaluated at the upper limit of integration. Okay, so because g of x equals the area of the region, the derivative is the rate of change of this area. So this is kind of an important sentence right here. The rate of change of area. That's what the fundamental theorem of calculus part 2 tells us. It is a rate of change of area. The derivative of an integral. A derivative is a rate of change, an integral is an area. So I'm going to put that right here. This is a derivative, and this is an integral. So that is what the fundamental theorem of calculus part 2 tells us, the rate of change of area. Okay, so we're just going to practice this. It's a great shortcut. We're going to go to page 2, and I'm going to do a couple of them the long way, just to show you that the shortcut does indeed work. And then we're going to do most of these with the shortcut. All right? So, in fact, let's do the first one with the shortcut. How do you recognize when to use the fundamental theorem of calculus part 2? You use it when you are asked to take the derivative of an integral. And the other thing that has to be there is that you have to have a variable for one of your limits of integration. So that's how you recognize how to use the fundamental theorem of calculus part 2. Again, when you're asked to take the derivative of an integral and one of your limits of integration is a variable, then you can use it. The shortcut simply tells us that we take that limit that is a variable and we plug it in everywhere we see t. So our answer is the cosine of 3x. That's it, done. Okay, that's the shortcut. Now we're going to do one the long way, just so that you can kind of understand that this indeed does work. Okay, so we're going to take this one and we're going to do it the long way. So the first thing we're going to do is we are going to solve this definite integral. Okay, so I'm going to go off to the side and I'm going to use the fundamental theorem of calculus. So the first step is to find the antiderivative. So the antiderivative of t squared is 1/3 t to the third. The antiderivative of 10t is 5t squared. Remember, if I take 10t to the second over 2, that's how I get 5t squared. We keep going. The antiderivative of negative 17 is negative 17t. All right, so that's the first step for the fundamental theorem of calculus, from 5 to x. All right, so now I'm going to have you guys ignore this for a second because I kind of need the room. We're going to keep going with the second part of the fundamental theorem of calculus. We need, hold on, typo, excuse me, thanks for bearing with me. We take g of our upper limit x, so g of x, minus g of our lower limit, g of 5. All right, so we are going to plug those in. So I take, this tells me to take my antiderivative, and everywhere I see t, I plug in x. So it's going to look like this. 1/3 x to the third plus 5x squared minus 17x. And then when I plug in 5, that's going to look like this. 1/3 times 5 to the third plus 5 times 5 squared minus 17 times 5. Now, really, this thing right here is just going to be giving me some number. All right, so that's the first step. We solve the definite integral. Now, when I take the derivative, if I take the derivative now, so now I'm going to take the derivative. Again, don't feel like you have to write this down. We're going to take the derivative. If I take the derivative of this term here, 3 times 1/3 is just 1. And then if I subtract 1 from this, I get x squared. So the derivative of this is x squared. Okay, now I keep going. The derivative of this is 10x to the first, so plus 10x to the first. And keep going. The derivative of negative 17, x is negative 17. And now I keep going. The derivative of this whole thing, the derivative of some number, the derivative of any number is just 0. Okay, so when I simplify this, this is my answer right here. I took the derivative of the integral. Now I want you to compare this. Let me erase this marking up here. I want you to compare this right here to the original integrand right here. It's exactly the same, but instead of t here and here, what do you see? You see x. All right, so we could have just gone right over here. I'm going to do this in blue. We could have just, to solve this, we could have just taken that upper limit and plugged it in everywhere we see t. So I plug it in here, x squared plus 10. I plug it in here, plus 10x minus 17. And that's exactly what I got here. So it does work. Isn't that shortcut nice? Much better than doing all of this work. Okay, now we're going to do the shortcut on all these. The rest of them, promise. Okay, right here, shortcut. We are taking the derivative of an integral, and one of our limits is a variable. That's our tip-off that we can use, Fundamental Theorem of Calculus Part 2, and we can use the shortcut. So we get the tangent to the third of x. You just take that x and you plug it in right there for t, and you are done. Ta-da! Shortcut. All right, let's do number 4. Again, we're taking the derivative of an integral, and one of our limits is a variable. That tells us we can use the shortcut. Fundamental Theorem of Calculus Part 2, we simply take that variable right here and we plug it in here. So it's equal to 2 to the x. Done. All right, now we're going to look at a different type of problem. Okay, what happens here for problem number 5 if we have something other than just plain old x? We have x squared here. What's going to happen is there's 2 steps here now. We are going to do the first step just like what we did above. We take that and we plug it in everywhere we see t. So that's the first step, 3 to the x squared. But now we have to take one more step. We have to multiply everything by the derivative of that limit. So what is the derivative of x squared? The derivative of x squared is 2x. And that's our answer. So if the limit is anything other than x, you have to multiply by the derivative of that limit. Now, let's go back up here. We really did that up here too. But hey, look, the derivative of x is just 1. So if I took this and multiplied it by 1, I would get the same thing. Same thing here. The derivative of this is just 1. So if I multiply this by 1, I just get this. So what you have to remember is if your limit is anything other than just x, you have to remember to multiply it by the derivative of that limit. So there's kind of 2 steps to the shortcut. I'm going to put them in right here. The first step, right here, plug in x okay, excuse me, I have to be a little bit more specific. You plug in your upper limit for t. So that's what we did here. I plugged in x squared for t. And then if your limit is anything other than just plain x, then you have to multiply by the derivative of the upper limit. Okay? So that's it. So we're going to apply that to the next one, problem 6. Okay, here we go. The first thing we do is we take that upper limit and we plug it in everywhere we see t. So we get the square root of the cosine of x. That's the first step. Fundamental Theorem of Calculus, Part 2. The second step, because this limit is not just plain old x, we have to multiply everything by the derivative of that limit. So the derivative of the cosine is negative sine of x. All right, to simplify that negative should absolutely go out to the front. So, and I'm just going to put negative sine of x, square root of cosine of x. Make it look nice and pretty. All right, there you go. Final, best full credit answer. So not too bad. There's just really 2 steps to that shortcut. All right, let's do number 7. Again, our upper limit is not just x. So we do the first step. We take that upper limit right here and we plug it in right where we see t. So we get the square root of 1 plus t squared, but instead of t, we plug in that whole upper limit, 3x minus 5. So there's the first step. And then, of course, because this limit is not just x, now we multiply everything by the derivative of this. The derivative of 3x is 3, and the derivative of negative 5 is 0. So we multiply everything by 3. And to simplify that, I would just put that 3 out front. 3 times the square root of 1 plus 3x minus 5 squared. And you don't have to simplify any farther than that. We're trying to use the shortcut and make things easier. There you go, final best full credit answer. All right, let's do one more, and then we will work on this week, and that will be our Fundamental Theorem of Calculus Part 2. All right, let's go to work. Okay, the first step is we take that upper limit and we plug it in where we see t. So I'm going to rewrite this whole function. All right, this gets tricky. All to the 7th, and then I have t to the 4th plus 1. So there's my whole function, but now instead of t right here, what do I plug in? I plug in my upper limit, x to the 3rd. So that's the first step. Everywhere you see t, you plug in that upper limit. The second step is we multiply everything by the derivative of this upper limit. The derivative of this upper limit is 3x squared. Power rule for derivatives. All right, so now let's simplify this. I'm going to put that 3x squared out front because you need the coefficient out front. And then I can also simplify exponents here. When you're raising one power to another, you multiply. So we get x to the 12th plus 1 all to the 7th. That was probably a little bit too big of a set of parentheses, but you get the idea. There we go. There is our final answer. Okay, so Fundamental Theorem of Calculus Part 2. We are taking the derivative of an integral. We are finding the rate of change of area. First step, you plug in your upper limit everywhere you see t into your integrand. And second step, you multiply everything by the derivative of that limit. All right, we'll be in touch, calculus. Take care.